thank the organizers for this. For this organization, it's always really nice to be here in Arpino. So this is not the title that there is in the program, because I decided a last-minute change to the presentation present today. But anyway, if you want to talk with me about the strain gradient and the stuff that is in the program, we will of course do it. So the work I will present today is related to a PhD thesis of this PhD student, Max Gattin, who just defended his PhD in October. And it is in a framework of a collaboration among the group of Laboratoire Modélisation et Simulation multi-échelle, multi-scale modeling and simulation laboratory, which is a joint lab between University of Paris Créteil, Université Gustave Eiffel, and CNRS in France. We are located in the Paris region, and the University of Liège in Belgium. So Max Gattin is a PhD student who performed most of the work, which was co-supervised by myself, Nicolas Boschut, who made this beautiful presentation. So I acknowledge him for this presentation, and Salah Naïm. So what is the context? We would like to use, I didn't read the title, but we would like to use metamaterials and properties from metamaterials in the framework of biomechanics. The context is the one of architectured scaffold, which are basically structures that are built to replace some large bone defects. When you have a large bone defect, you need to replace the defect with some scaffold that is able to fulfill several mechanical and biological properties. And what we would like to do is to play with this scaffold as it was a metamaterial, because this is quite an emerging topic since the advent of additive manufacturing. So you can really do this kind of implants. You can play with architectures, with we will see on the right scale to be used with for interacting with acoustic waves. And what we want to do is, on one side, to understand what's happening and why these materials are working, and also, as we will see, to be able to control the state of the material and the biomechanical integration with acoustic waves. So the general context is that we want to, one may want to improve the long-term structural integrity of this kind of implants once they are inserted into a host bone. And the features that play a role are, of course, the implant must be biomimetic, means that we replace the bone with something else, and the best choice would be to have a material that has the exact same properties of the bone we replace. And this is not usually the case. I don't know if you are familiar with orthopedic implants. They are usually built of bulk titanium, so much more rigid that bone that you are replacing. We're talking about 1 order of magnitude in terms of stiffness, and so they can basically the implant carry too much load. The surrounding bone is not loaded and can resorb, and so you have this kind of effect that is called stress shield. The implant must promote osteointegration with what is called osteoconduction. Osteoinduction means that the cells can penetrate into this porous implant and colonize and build mature bone inside, so that the bone can attach to the implant. You can have implants that are biodegradable, either metallic or ceramic or hydroxyapatite. And finally, you also have to ensure, of course, biocompatibility. So in order to obtain these features, you can play with several basic ingredients that affect in a very complex way what's happening in the implant. So this is a scheme where there are a lot of arrows to see that everything is interdependent. From a mechanical point of view, and from the point of view of metamaterials, we will consider basically that we can choose the green ones we are playing with some metamaterials, so we can, with some architectural materials, so we can choose the constituent material, we can choose the geometry, the size, and the porosity, and this will have an effect on the other properties. What we are looking for in the whole picture is to have an optimal balance between all these properties in order to have an implant that is well accepted into the bone and perform its duty, which is the final object. In terms of, just to give some data, constitutive material of the implant could be metals, ceramic, biopolymers. The unit cell geometry can be random in the sense that it cannot be. They also produce random materials, so no unit cell. Cubic, diamond, gyroids, TPLS in general. What is important is that the pore size that is needed to have these properties and promoters to induction, for instance. You must not have pores that are too small, neither too large. So it's around 100 microns and millimeters, and the porosity is between 30 and 70%. This is to replace what is called sponge bone, trabecular spongy bone. The state of the art that I represent just after will only concern this part. I will not talk about the more mechanobiological part. Okay, even if we are doing this in the team, in the biomechanical team, in the laboratory, I will not talk about this in this presentation. So what is the state of the art of the evaluation of this new kind of implant? Basically, in the works that can be found in literature, you choose a geometry, it can be like a or something, then you build your scaffold, and this is titanium with laser sintering techniques, and you implant it into an animal model. So sorry for the disturbing image, but this is a needed step if you want to understand if this is really working. So the scaffold is here, and then to evaluate if it worked, you usually do histology. You take the implant, you cut it in slice, you slice it, you put chemicals in order to see where the cells are. You do micro CT. That cannot be done in vivo, so you have to harvest the implant and you can see where the bone is formed and so on. And in order to access the mechanical properties, you need some kind of pressure test or pull-out, push-out test on the implant. The characteristic of these tests is that they are almost empirical, they are destructive and poorly reproducible. So, and you also have not a limited number of time points because the cicatrization happens in weeks, and you cannot, also for ethical issues, you cannot have a lot of, since you have to sacrifice the animal to extract the implants, you cannot have a lot of time points. Usually you have like 3, 7 weeks, 21 weeks. So what we want to do, we want to develop a method for a non-destructive evaluation of the state, let's say, of resorption or osteointegration of the implant by leveraging on the fact that basically this implant is a metamaterial or a phononic crystal. So it's something that interacts with ultrasonic waves. It's something that is called also in the literature biometamaterial. So how do we do that? And why do we call it metamaterial? Because if you look at the very large literature about metamaterials, even I think in the literature no one agrees on what a metamaterial really is, but in the community of wave propagation and acoustics, let's say that you can play with two concepts which are phononic crystals and elastic metamaterials that, in my opinion, are quite entangled. But let's say that metamaterials can be used in many fields of application and over a broad frequency range that basically depends on the size of the element that you're analyzing. So here we will work around the megahertz, which is the frequency of medical ultrasound and corresponds to an interaction with structures that are of millimeter size. So since our structure are millimeter size, the choice of the megahertz is the right choice, and it's good because we already have the equipment to measure this kind of waves. And of course, why do we build metamaterial? Because the material design can be tailored to affect wave propagation and control elastic waves. And there's a huge literature on this. So just to illustrate what's happening to a wave that propagates inside a metamaterial, or in this case, I should use phononic crystal because there are not internal resonances, but this is just an illustration. You have, to describe the dynamic behavior of a metamaterial, you can use this diagram, which is the dispersion diagram, where you have the wave number here and the frequency here, which is somehow the fingerprint of the elastic architecture material, let's say. Which means that it will characterize its dynamic behavior. And this point here corresponds to low frequency and very large wavelength, and you can see that there is almost a straight line at the beginning, and this is the behavior you have when you propagate in an homogeneous material, a linear relationship between phase velocity and wave number. So what happens if you use a classic transducer, which is centered over a central frequency, but it has a bandwidth, and you send a wave in this range here, you have that, you see, this is not a straight line anymore, so the wave packets, depending on the frequency, will travel at different velocities, phase velocities and group velocities, and so the packet will distort as it will enter the metamaterial and will go on the other side. This will be the experimental setup that we will use later in the experiments. So you have an emitter, you propagate in water, for instance, you have your medium, your specimen, and then you have a receiver. So if I play another one, you see that the wave is distorted, but then goes out with a different form, but it goes to the receiver. If you go upper in this region where there is no black line, meaning that there is no purely linear solution for wave propagation, you have a very well-known phenomenon, which is called bandgap, which means that in this region, when you excite a wave that has a frequency in this region, you will not have propagation inside the specimen. This doesn't mean that the wave will be damped. It means that it just cannot propagate. So in our configuration, you can see that the signal is emitted and just cannot enter the material. It is completely reflected. Usually this kind of feature is widely used to damp, or let's say to optimize the fact that the receiver, you can see, is not receiving anything. We will use it in another way. We will exploit the fact that you have a big reflection when you enter the bandgap. Okay? So much bigger than the reflection you have when you are outside the bandgap. This is the feature that we will use from the ultrasonic point of view to analyze the behavior of the material. So going to the objective of the study, and we have the same picture as before, we want to know when the implant is inserted into the bone. This is a much exaggerated implant, they are much smaller. We want to put an ultrasonic probe and be able to test the material in a non-destructive fashion. And in order to do that, we want to tune the microstructure and mechanical properties of this implant, to tune its acoustic behavior and create some kind of acoustic signature, which we suppose to be proportional to the feature we want to follow, post-integration, for instance. And we want to do monitoring by following this quantity. Okay? So during the thesis, in order to arrive at the proof of concept that we present to you in this work, we did some preliminary studies to study the effect of viscoelasticity, for instance, because these materials are highly viscoelastic. We had to identify which kind of ultrasonic signature we want to use, and we decided after a while to use only reflection, because we cannot measure transmission when you imagine that we are putting this probe in a bone, so you have outside the skin, So you will have a thin layer of soft tissue, and it's much easier to measure the reflection than the transmission on the other side. And we wanted to do an experimental validation of this. So not only numerical simulation, to arrive at some kind of proof of concept. So we did some simplification in order to do this, meaning that in this first proof of concept there is no biology. We built some kind of artificial system that is supposed to mimic the behavior of the implant and of the bone. So we use this paradigm, which is if you consider the scaffold to be a hard matrix and the bone ingrowth and mineralization inside to be some kind of soft inclusion that can vary in size and in stiffness. And so we have to play with the viscoelastic periodic biphasic structure that displays sub-millimeters 1D or 2D cells. And something like this, basically. This will be the size of the specimen. We will have a plane wave arriving on this specimen where you have some kind of 15 or 20 unit cells in the specimen. There are basically two materials, one softer and one more rigid. And we will play with the inclusions, which will be, let's say, the unit cell will be very simple in this study. It will be a square unit cell, and the inclusion which represents the bone will be growing inside. Okay, so we will have unit cells with more and more black material inside, or unit cells with the inclusion of fixed size but with increasing stiffness. So why do we play with this kind of configuration? Because this is why we started the collaboration with Liège, because you can print this kind of material using a polyjet 3D printer, which is able to print almost like an inkjet printer on paper, multiple materials and gradients and also combination of them, but we will use two materials, an elastomer, which is called Tango Black, which will be black and is very, very soft. It's really an elastomer in static properties. When you put waves inside, it's much more rigid. And a glassy polymer, which is called Vero White, which is much more stiffer. Okay? The acoustic impedance contrast is not so high. It's 1.4, 1.7, so we are really playing with not a lot of contrast with respect to, for instance, if we would have used titanium or other kind of material. And the box set size is very precise. And finally, we end up with this very simple geometry. The unit cell is around 700 microns. And inside, you have an inclusion of the soft material in the rigid material. This is what it looks like once printed at the microscope. So this is 1 millimeter. It's not perfect, but we will see that the thing that we are studying, let's say the band gaps, are quite robust with respect to this kind of imperfections. And I forgot to take the samples with me, but the sample looks like this. There are small plates with holes. So this is a 3D structure, but it's it is an extruded 2D structure. So it's the most simple case you can consider. And we play it with some volume fractions, which is supposed to be the equivalent of time. At the beginning, you have a full implant. Let's say this is the beginning. Then the implant gets resorbed and the bone grows inside. And we want to know if we can follow this evolution of the volume fraction by measuring the acoustic properties. So first of all, we did a block theory analysis on a unit cell, which means that the material is supposed to be infinite, viscous effect are negliged, and you put periodic boundary condition with this phase coefficient that corresponds to the propagation of the acoustic wave, and you obtain this kind of diagram, which you see wave number and frequency. It's much more complex than the one I presented earlier, but it's quite disappointing because there is no band gap, or there is no full band gap inside. This is because this material is this geometry is very, very simple, so there is no full band gap. However, if you look, basically these are the eigenvalues of the solution of an eigenvalue problem, if you look to the eigenvectors, which are the polarization of the waves that really propagate inside this material, you find that some of these modes are symmetric. This is the shape of the deformation of the unit cell as the wave propagates through the material in the horizontal direction. Some of them are antisymmetric, some of them are symmetric. And so basically we can discriminate between modes because we have the specimen will be inserted in water, so the only incoming wave will be a longitudinal polarized incoming wave from left with a normal incidence. So basically this wave can only see the symmetric modes. So if you play with some average of the field, you can end up with a observability coefficient that makes you see that the wave, our longitudinal wave, can only see this dotted point solution, and so actually you have an elastic bandgap for longitudinal waves. So once we identified this bandgap, this zone that we want to use, we did the analysis for different size, and you can see that the bandgap shifts in position and in width. So this is encouraging, meaning we change something that is supposed to be correlated to the biomechanical behavior, the bandgap evolves. And this is this is the diagram of the bandgap in function of the volume fraction. So again, the objective is not to optimize the bandgap to dump something, it's just to see that we have some kind of sensibility, so the slope is not zero, and that we can expect to follow this bandgap to follow the volume fraction. So once we validate this for an infinite medium, we still have the problem that in experiments and in our application, we will have a finite specimen with 10 cells, 20 cells, and we'll have viscoelasticity. So in order to validate this, and also we want to play with the reflection coefficient. And here there is no way to compute the reflection coefficient from block analysis. So we did a finite element simulation in harmonic regime where we consider perfectly matched layer, an incoming plane wave in water, our specimen, which is a finite specimen, and then we wanted to measure the reflection coefficient. So the result for one given volume fraction is this one, reflection coefficient, transmission coefficient. You have a drop of the transmission coefficient as it is expected when you enter the bandgap, and you also have a peak of the reflection coefficient when you enter the bandgap. If you play with we played with the volume fraction, and you see an evolution of the bandgap, and basically what you can observe already is that this peak in the reflection coefficient always follow the end of the bandgap, and this is what we will try to exploit as an acoustic signature. So experiments. So once we validated the simulation part, which was not easy because we had to do experiments to calibrate the properties of the printed materials, we performed the experiment in a water tank. So there is a probe here, which is the emitter and the receiver, which we send a signal that will propagate through the sample, we reflect at the surface, and then we measure the reflection. So we don't care about the transmission. We measured it, but we didn't use it. So this is the output signal, and then the signal processing is very simple. Fourier transform of both. You take the ratio, and you have the reflected signal. So these are actual measurements. What you see here. So it's quite simple. A simple. Let's say, experiment to describe. It's not so simple to realize it. And there are distributed degrees. So if we put a chart, let's say, of the volume fraction here and the frequency response here for different volume fractions, you have this zone of high reflectivity, which basically corresponds to the presence of the bandgap. And all the graph I will be presented will be slices of this graph, which means that we perform the experiment on one configuration, and we have the frequency response. And the simulations for different volume fractions, you can do 70, 29, 18, and 8. These are the position of the band gap as it was forecast by block frequency analysis. So you see that the peak in the reflection is always at the end of the band gap. And these are the experiments that are quite satisfying. I mean, there's quite an excellent agreement between the experiments. These are performed at 2 megahertz. I forget to put the scale, the wave, let's say the central frequency of the transducer is 2 megahertz, but you can see that it's quite broadband. So basically, following these reflectivity peaks, which can be discriminated, we can follow the volume fraction in a non-destructive way. The frequency of the frequency of the reflectivity peak decreases as the volume fraction increases. And so we do expect that this ultrasonic signature can be used to follow the state of implants. So we perform this kind of test. What I showed to you is the tracking of the bone ingrowth, going from this side to this side. What we've done also, but we didn't show you, is the tracking of bone mineralization if the inclusion band becomes stiffer and stiffer. And what is interesting is that one could say, okay, but basically you are going from here to here, you are lowering the overall stiffness of the implant. So you could measure these properties also from statics. I mean, with a mixture low, you can say that this is stiffer than this one, so you see that the velocity is decreasing. You can do some kind of measurement of that without needing the ultrasonic response. And this is not true, because if you put every sample, for instance, on this chart where you have the volume fraction and the equivalent stiffness coefficient obtained from classic homogenization, you have that, okay, there is a separation, but some configurations are almost confused, meaning that two very different configurations have almost the same stiffness, and this cannot be discriminated using only low frequency values. I'll go fast on that, but the acoustic behavior, it's at high frequency, it's able to discriminate cases that when you homogenize have exactly the same elastic properties at low frequency. So the low frequency part of the graph, it's almost superposing. The high frequency is not. But anyway, since I have to conclude, what we are doing now, once we have, let's say, validated this concept, of course, we are trying to complexify a little bit the behavior. And for instance, we want to study some kind of rainbow effect. I mean, once we validated the fact that we can treat this kind of medium as a metamaterial, we have a huge literature of exotic behavior that we leverage. And for instance, rainbow effect, Willis coupling. We will, of course, play. We already started to play with some complex geometry to have real band gaps, play with chirality, with TPMS, and so on. And we are also planning to do this on real implants, titanium implants printed in 3D. And we submitted a project to do this also up to the animal testing and so on. And that's and the objective is to have a structure that promotes osseointegration, amplified band gaps, and the sensitivity of the band gaps with respect to the evolution of the properties of the soft tissue that is mineralized. Okay, thank you very much.